I should add to that very, very fine introduction by Marcus that the company is called NI. But yes, we are the EDIS research group. Yeah, I'm going to talk about GPIOs and USRPs. Now, this seems like a very, very basic low-level topic, and it is. I usually try and sneak in at least sort of one background, just like fundamentals of SDR topic. And the GPIOs on our devices are something we get a lot of questions about. So yeah, this will be hopefully like kind of a useful guide for everyone who's like ever used or planning to use GPIOs on USRPs. All right, let's go right into that. So first of all, just to make sure we're all on the same page. What is a GPIO? So a general purpose IO, as Wikipedia states, is an uncommitted digital signal pin, which may be used as an input or output and can be controlled by software. Now, actually, does the laser thingy work? No. Yeah, I'll just gonna. Can I enable the laser thing, Mark, without like messing up your AV setup? Let's see if I can figure out how to do that. I don't know how to do this. I'm just gonna keep going, whatever. Yeah, so if you've ever bought a Raspberry Pi or an Arduino, then you have like all of these pins. Those are GPIOs, and the whole point of those is that you can do whatever you want with them. Now, on a USRP, we also have them. They're like these pins in the middle, and really, in a very real sense, they're the least interesting connector, right? We have like 100 gigabit Ethernet and multi-gigahertz analog signals coming in and out, but we still get so many questions on these GPIOs that I thought it would be worth talking about them here at the conference. All right, so. I don't know everyone's, but for many people, like your first electronics project was like blinking an LED. So can we do that? We'll just plug it in the USRP and get going. And I'm gonna stop everyone right here. Like, don't do that, please don't do that. Now in this particular case, nothing would probably happen. I don't think you can break the USRP that way, but you can break the USRP by misusing like GPIOs. So here's like rule number 0, like just always stick to that. Like you don't want to sink a lot of current into a GPIO. You don't want to draw a lot of current from a GPIO. 5 milliamps should be your budget. Try and stay below that, especially if you're using many of those. Like just don't do anything like that. Like this is actually one of the ways you can fry a USRP. And then it's gone. Like, and that's not covered by warranty either. So, yeah, be careful, please. All right, but honestly, this is not so different from other, like I said, other devices like Raspberry Pis. So that's fantastic because that means there's a lot of guides on the internet available. If you can't draw a lot of current and you want to drive an LED, for example, what do you do instead? Well, rule number 1: BYOP, bring your own power. You need to somehow. Provide power so you can actually drive stuff, and LEDs are just an example here. Doesn't matter what it is, and make sure that your actual GPIO is sort of removed from the circuitry. Well, it's not removed, but it's like somehow decoupled. So a good way to do that is use Darlington transistors, have high amplification. So this is the simplest possible circuit that I could come up with to drive an LED. So on the right hand side, you have your own power supply. You put current through an LED, and then the GPIO can open or close this transistor basically based on its state, and then that's it. So this is a good way to get started with GPIOs. Let's see, there should be. All right, now we need a little bit of software to set up the USRP to make the LED actually go blinky. And so this is like a short snippet of Python that'll do that. There's a few lines up here that'll actually configure the pin to be in the state that you want it to be. And then we have this loop which goes up to 11 naturally. And then we just like write a 1 or a 0 into a register, and that'll like drive the GPIO high or low, which in turn will turn the transistor on or off, which will make the LED blink. And this is, let's see if this works. Yeah, this is a video. So it should blink 5 times, 3, 4, and 5, because like we have 11 flanks here. So yeah, that works. So blinking is fine. Great. Now, blinking an LED, I mean, it's cool and all, but you don't need to buy a USRP. I mean, you can, I wouldn't mind, but there's like much cheaper ways to do that. And also you don't have to go through these weird APIs that we provide. So if you want to blink an LED off a Raspberry Pi, there's like 1,000,001 tutorials on the internet. So why would you do that on a USRP? And one of the reasons is that those pins are actually useful not just for sending like a software command to turn them on or off, but also this feature here, tracking the radio state. And that's like a really, really key feature, and I definitely want to make sure that you all know how that works. Now this is the ATR feature. Now, to blink the LED, we had to write a 1 or a 0 into a register, and that's the one at the top, like the GPIO out register, the sort of not quite so bright yellow one. But there are 4 other registers that you can also write to, and those follow the state of the radio. And this is a key feature, so I'll make sure you pay attention now for the next 30 seconds. A radio can be in one of 4 states. It can be idle, it can be transmitting, it can be receiving, or it can be transmitting and receiving at the same time, full duplex, okay? So if you don't care about that and you just say, I'm going to write like 1s and 0s into that register to turn the pins on or off, you can do that, that's fine. If you do this ATR thing, then you sort of pre-select the state of your GPIOs based on the state of the radio. So at an early time in your program, you say, okay, whenever the radio is idle, I would like my GPIOs to look like this. And when it's transmitting, I want my GPIOs to look like this, and so on and so on and so on. And then the actual state switching happens on the FPGA at real time. So you don't have to, from software, control how that works. So how does that look in practice? So if you've ever used a USRP, then you've probably noticed that under the SMA connectors, or next to them, depending on which device you have, there is some LEDs that turn green or red when we are transmitting and receiving. And you might have wondered, like, how do they do that? Like, how does the LED know when we're transmitting or receiving? And internally, we have the same GPIO API. It's just not exposed to users. But if that's what's happening, maybe we can build a little script that mimics those LEDs. So can we like follow the state of that LED with my external LED? And this is how we do that. Here's again a little Python snippet on the right. And the interesting bit are these 4 lines here that have this ATR thing in one of those arguments. So you can read it as follows, like 0x is the idle state. So we say when the radio is idle, we want GPIOs to be off. When we're receiving, we want the first pin to go high. When we're transmitting, we want the second pin to go high. And when we're doing both, we want both pins to go high. And then we sort of step away and say, now go. And in this script, we're going to do a receive 1 second, and we're going to do a send 1 second to see if that works. And you can follow the LEDs here next to the SMAs to make sure those are the ones that we're trying to mimic. And I put this on a loop. So, when we receive here, this LED will also turn on. When we transmit, you can see it here. This LED will also turn on. That's how you do that. Now, why on earth would you do that? Like, you may want to build like one of those on-air signs or something like that, but that seems overkill. This is really useful when you're controlling something like an antenna controls or external amplifiers or something like that need to know when you're actually transmitting. This is how you use that feature. And that's really one of the main reasons to use GPIO on a USRP. Okay, so that's most of the basics. I'm going to go now. Before I go into the really interesting stuff, I need to talk a little bit how you actually connect those GPIOs on the USRPs. And this is like the most boring section of my presentation, so I'm going to rush through it as fast as I can. Actually, I have plenty of time, I realize, so I don't have to rush. Yeah, okay, I'm just going to go through the various connectors. We have a lot of diversity. This is one of those cases where diversity might not be helpful. But anyway, gives me something to talk about. All right, I'm going to start with the X310 and the N310 just because I used them in my examples earlier. So if you're my age, then you might have had a computer at some point where you had like one of those DB15 connectors where you plugged in a joystick. And those are the same ones that we use for exposing GPIOs. So there are 15 pins in a DB15 connector, 12 of which are GPIOs that you can use for your whatever you want to do. And they're all at 3.3 volts. So if they're high, then they are at 3.3 volts. And if you want to sort of start playing around with them, I recommend getting one of these breakout boards. You can see at the top, this one that we actually sell through our own shop. That's for, mostly for people who want to get like a stash of stuff like from the same vendor, because you can get like, you don't need a special one. You can, if you're lucky, and you can get one like really cheap off of, I don't know, Adafruit or something, then that'll work just fine. Also depends on what form factor you need, etc. How much you actually want to expose. By the way, I didn't put this on the slide because I didn't want to, but if you're in a pinch, you can just put the jumper cables like from a breadboard straight into the DB15 connector, but please be careful. Okay, that's not recommended operation. All right, our flagship USRP, the X410, I only didn't put that first because I wanted to start off with the ones that you had seen earlier in the slides, is much better designed when it comes to GPIOs. First of all, we have 2 connectors, which gives you more pins, 12 pins per connector, 24 pins total. And then they're on an HDMI connector, which is just a much better connector, more common. You can also get breakout sets for HDMI, that works just fine. And we have a bunch of cool features that we didn't have in the past. So we've been evolving like sort of the GPIO functionality along with all the other features, like bandwidth, etc. But this is sort of a usually less talked about one. So for example, we have a dedicated pin on those HDMI connectors that you can actually draw power from, so you don't need to bring your own power supply, which can come in handy in some cases. And you can also switch the voltage. You can get much higher switching speeds. I'll talk about that later. And another thing that I'll talk about later is there's sort of a built-in hard SPI mode for people who want to control peripherals that use SPI on the other side. But I'm going to talk about that towards the end. E320 also has an HDMI connector. It's a mini HDMI connector. But if you have a mini HDMI to HDMI cable, you can use the same breakout boxes, etc. It's very neat. You only have 8 pins though on the E320. And we don't have any software support for switching the voltage there. Even though it's theoretically possible. If that's something you need, then you can talk to us. The E310 is probably our worst offender when it comes to GPIOs. Like I said, this is something we evolved over the years, and when we built the E310, this was not on the top of our minds. But to get to the actual connector, you have to open the box, which is I'm not gonna lie, is a disadvantage. And the connector is also not the most common. I think it's 2 mil pin spacing connector. I don't know what the name of the connector is, but there's some nice features there. So for example, we exposed the regular 3.3 power rail through that, which means you can actually draw power from there. But be careful, this is not dedicated to the GPIO, so you can actually brown out your device if you draw too much. And you have 8 pins available to do the usual stuff. B200 series. So the mini series, and mini is like the name implies, is a very small USRP. So the connector is also small. Most of you would probably do best by getting one of those adapters that expose a 12-pin, 100 mil spacing standard GPIO, thing. Looks like on a Raspberry Pi or something like that. The regular B200 series, the ones with the Euro card size, they don't need that. The connector is directly on the board. Although there are some revs where that's not populated, and you have to hand solder it down, which is not difficult though, by the way. Just in case you're curious. So I highlighted all the locations where they are, and then you can look in the manual for the specific pin assignments. And finally, if you're using the really old USRPs, this is an API we've had for a long time, you can actually use daughter boards to access GPIOs. This even works on the X310, but on the older USRPs, we don't have a dedicated separate GPIO connector. So yeah, this is definitely useful for those scenarios. Okay, that's the connectors. Now it's going to get a little bit more interesting. So I'm going to have to go through a couple of concepts here. So if you're used to programming GPIOs on a Raspberry Pi or something like that, this is where it actually gets a bit different. The circuitry design, etc. That's all very similar. You can use existing designs from other projects that are not specific to SDR, like decoupling your GPIOs, etc. But here we have a couple of things that are more or less unique to the way we've implemented this. Okay, first of all, remember this little picture here at the bottom. This is the when I was explaining how the ATR registers work, we have 4 registers, and then we have the actual manual GPIO register that we can write to. All of that is what we call a GPIO bank. So that's the first word that you have to remember. And we have usually more than one of these banks per radio. So a radio is any part of the device that can transmit and receive. So for example, on the X310 and the X410, we have 3 of these banks. We have one for TX, one for RX, and one for the front panel connector. And they are actually physically connected to the TX connector and the RX connector and the front panel connector. So despite the name, they all support all the radio states. So you can say the TX connector GPIO state should also change when we're receiving. That might be useful because you need to, I don't know, do some isolation something. So these are completely programmable with respect to those states. So yeah, so we have 3 of those banks, but you might ask, wait a minute, okay, this makes sense, but there's 2 radios on the X310, so what about that? And the answer is yes, that's correct. And all of those banks are duplicated, so we actually have 6 of these banks that you can program. And in the USRP X310, we have like the A side and the B side. So there's a TX connector on the A side and there's a TX connector on the B side, but there's only one front panel connector, which means this bottom register here, FP0, that's just its designator in software. Like we have 2 of these registers, or banks, sorry, now I'm confusing my own terminology. We have 2 of these banks connected to the same front panel connector. So how do we arbitrate that? And we have the concept of a GPIO source, and we have 3 APIs for that: get GPIO sources, get GPIO source, and set GPIO source, which you can use to query available modes, the current mode, and then obviously set one. Now I mentioned earlier the X310 has 12 pins. For each of those 12 pins, you can decide who's going to drive that. Is it going to be radio 0 or radio 1? So that's freely configurable, but it can only be one at a time. So you could say like the bottom 6 pins go to radio 0 and the top ones to radio 1, or I'm just going to assign them all to radio 0 or whatever. That's all up to you. All right, but that's not all the available sources we have. If you look at the USRP N310, for example, we have 2 channels per radio, which means we also need 2 banks like per radio. And that means we already have 4 of these registers that are all potentially able to drive the front panel connector. But we have another mode, which is the PS mode, like that's the processing system mode. And that's a mode where we yield control of those GPIOs to software that is not controlled by us. And that's when you go back to like sort of the Raspberry Pi programming mode. So you can say, okay, front panel connector, I don't know, top 6 pins, I'm just not going to care about those. Like I'm just going to hand them back to the user to, have some random software running on the device to control those. But otherwise, it's the same principle. And if you go to the USRP X410, our current flagship product, which you can, by the way, take a look at our booth, we have 2 front panel connectors. So it gets yet a little bit more complicated, but only a bit, because this API call, set GPIO source, takes multiple arguments, and it takes, one of the arguments is like, which connector are you actually setting the source for? So basically this API, you say, for front panel connector 0, I would like pin 0 to be assigned to radio 0, and pin 2 should be assigned to radio 1 or something like that. One thing that I forgot to mention, depending on what kind of API you're using, there might be a requirement to uniquely identify all of these banks. So if you look at this slide, for example, I put in parentheses like the unique name that, for example, the multi-USRP API understands. Because, if you're saying I want to program the register FP0, is like which one are you talking about, the top one or the bottom one? And that's how we differentiate those. Okay, so how would this actually look like in software then? So this is like the shortest snippet that I could come up with that sort of shows off all the available features. So again, I'm like in this specific example, I'm talking to an X310 or an X300, which you can see on like one of the 3rd line. And first of all, I'm going to query. Oh, wait a minute. No, there's one thing I need to mention here. On this slide, I mentioned that you pass in the name of the connector and the name of the source into the API to say which pins should be controlled by whom. And this is one of the things where I'm like going back. I would like to rename this API. Obviously, we're not going to do that. It would break people's applications. But we use this word banks like twice. Like once for this like yellow box on the left, which is the register we're talking to. But also then we have this thing called a source bank. We just should have called it connector in retrospect. So that's a little bit confusing. The manual has like a huge, bold-faced things. This is not the same as that. Like here's an example of how to use it. So I think if you read the manual, you'll be fine. But like the API naming could have been a bit better. So you can ask the device by calling get GPIO source banks which connectors are available to you. And that's what we're going to do here. So we're going to first ask the device which connectors are available, and then we're just going to pick the first one. And because it's on an X310, there's only one connector, which means this variable db15con name will now contain like the identifier that we use in software to identify the db15 connector. So we're just going to use that in the following. So, and then in the next line, we'll say, okay, Mr. db15 connector, can I please have 8 pins assigned to source RFA and 4 pins assigned to source RFB. And those correspond to the individual radios. So you might say, why aren't they just called radio 0 or radio 1 or something like that? And that's because there is a distinction between the physical sources in the FPGA and the actual RF knock block. So because you could potentially rewire them. I highly recommend not doing that, but something that you could feasibly do is just remove one of the radios because you need to recoup that FPGA space, and then that name would no longer be available, but the pins would still be available. So that's why they have different names here. Okay, so now we're gonna ignore the top 4 pins. So we can set a pin mask of just 8 pins. So that's here the pin mask. And then we're going to go through a couple of exercises. So first of all, we have a register called control, which decides whether or not a pin is tracking the radio state, and or if it's to be controlled by the user. The DDR attribute defines if it's an output or an input. You can see I have 2 pins defined as inputs. A 1 is like if it's a 1, it's an output. If it's a 0, it's an input. And then the 4 states. So I'm basically doing a one-hot encoding of my radio state onto the GPIO. So I have 4 pins available to track the state, and basically one of them will go high depending on which state I'm in. And then at the bottom, you can see an example of me programming like the specific pin that I can manually set, like through software, but I'm using a time command to do that, which means I can very, very accurately decide when a GPIO pin will go from 0 to 1 or from 1 to 0. And then the last line, I'm actually reading back a GPIO. So like if externally I'm like monitoring something and I just want to know if this is 1 or 0, that's how I would do that. Okay, so there are 2 things that I decided to not put in my presentation. I just couldn't fit them in time-wise, but I just want to mention them here, and maybe I'll do a longer one of these at some other event, or I don't know, on YouTube or something. The first one is, I mentioned earlier the X410 has an API to control the voltage of the GPIOs. And it's explained in the manual, so I'm not going to talk about it here. And the second one is I also mentioned that you can yield control of the GPIOs to software when you're running on the embedded devices. And we use a standard kernel API. And there's a Python package called GPIOD, which is installed on the device, which you can use to just control them. So you can just write Python code to directly talk to the GPIOs without having to go through UHD. Okay, finally, protocols and signals. This is where it gets really interesting. Now, blinking LEDs is nice to get started, but that's not really like the killer feature. So what am I talking about here? Okay, I mentioned already that we can use time commands to set GPIOs to go high or low. Now, here's a code snippet at the bottom where I do exactly that. So this is actually similar to the LED blinky code snippet that I showed at the beginning. However, I am using this set command time API to decide when those toggles occur. And I want to generate a 1 kilohertz signal here. So like at exactly multiples of like my period, or like half the 1 kilohertz period, I'm either going up or down. And here's sort of a scope capture where I'm putting cursors on the down flank and the up flank, and you can see it's exactly 1 millisecond apart. And you'd say, well, 1 millisecond is like, that's not that fast, that's not that interesting. But you have to keep in mind that this is going over the network and it's like controlled by some Python script. So I don't have any kind of scheduling on the software side here. And yet I still achieve like that very exact flank. Now, if I can do that, then I can also let all the other pins go up or down, depending on what time I want them to do something, which means if I have multiple pins, I could, for example, implement an SPI transaction this way, where, I have one pin, that's the SPI clock going up and down, and then, a chip select goes high or low, whatever, depending on what I needed to do. I don't know, half or full clock cycle before the transaction starts, and then I have my actual SDO, SDI lines that I will read or write to. So, and if we write software to implement like a SPI transaction or something like that, we call that bit banging. So that's something that you can do with very high accuracy, but not with high speed, because you still have to like push all those commands to the device. So you're speaking of like kilohertz range, but that's still useful for many peripherals. There's another reason you can't go super high in the speed, which is not software but hardware related. Like in the bottom, I've actually zoomed into one of those flanks. You can see it's not perfect. It takes a while to sort of, go up and then become one. And it's the same is true on the way down. So takes about 40-something nanoseconds here. We have two flanks, rounded up a bit. It's approximately 100 nanoseconds of like transition time, which means that we can't go below that, which means that sort of limits our rate that we can switch up and down at, which is approximately 10 megahertz on these devices. On the X410, like we took great care that that's not the case. You can switch you can toggle these pins at up to 100 megahertz on the X410 without running into these kinds of problems. But then how do you do that if the software is still slowing you down? And we also have a solution for that. So if you want to do an SPI transaction specifically, we now have additional features on the device similar to like a hard SPI core and like a microcontroller that you can just use to say, okay, instead of saying, hey, I want this pin to go high and then low and high and low and blah, 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 you can just say, okay, this is my SPI transaction, take care of it, and clock it out at whatever rate that, I configure it to. And you can do that. So you're limited to about 100 megahertz, and the actual SPI clock that you can use is always an integer fraction of your radio clock. So in this example, let's say you run at 250 megahertz, so that would be 250 megasamples coming in and out. Then you can say, okay, I'm going to divide that by 4, gives me 62.5 megahertz, and then that's my clock speed. So you can do pretty good stuff, not just timed, but also fast. And this is really interesting when you're talking of things like antenna control, like something like, antennas that require code books or something to actually set up with, something that's more interesting to control. Yeah, that's when you would really want to do that. This API is not exposed in Python yet. Talk to us if that's something that you need, but it's available through C++, and it's pretty well described in the manual. I put a screenshot here. All right. I try to leave a little bit of time for questions. So if you have any, I'm very, very happy to answer those now or later. This was, like I said, a very basic intro talk to GPIOs. I could have given the same talk probably 5 years ago, but I hope this will like clear up some questions for some of you. Okay, thank you very much.
So we have one question from the audience. I'm directly handing over to you.
Thanks for the presentation, very good. I have some experience with the GPIOs, and maybe it's more of a comment / question. Is there a way to, like, you can use the ATR feature, but also configure for the GPIO transition to happen like slightly before or slightly after the radio switches state? The way I've been doing it is I use the timed command, but then it's a little bit more work. You can't just trust the radio to do it in hardware. You have to do it in software, and it's a bit more.
I'm sorry, that's not possible. The pin. I mean, what you could do is you could like put that delay. If you want to do slightly after, you could put the delay in your circuit, in the electronically. But yeah, like especially slightly before is difficult for obvious reasons. Yeah, I mean, we could probably have a delay in there somehow, but that doesn't come up a lot. So you could probably like have a shift register or something to do that in hardware.
So we have another room question.
First of all, many thanks for the presentation. It was very interesting and explained a lot of things that were a bit fuzzy on the online documentation. When trying to control the pins over software, right, using the huge drivers, Python API, or even in GNU Radio over the asynchronous message interface, right? What kind of delays should we be expecting from issuing a command to seeing the ping being toggled?
Okay, so you're asking about the delays, right? I'm guessing between sort of software and hardware. So it's similar to any other command, like set frequency, etc. Like you should give it like several milliseconds ahead of time, because in software we sort of packet up the command, and an Ethernet packet has to go over the network and then has to get unpacked and then it goes into the radio. That's where like time commands come in really handy, because you can say, okay, like I can plan ahead a little bit. This has to trigger at exactly this time, but I know like 10 or 20 milliseconds or even like a full second ahead of time when that needs to happen. That's when that comes in very handy. If you like my first example, or this one here where it's just blinking in a 1 second, like I don't have any, I'm just like sleeping in Python, and you can see it works okay, but like we're talking of like 50 to 100 millisecond like jitter, and you probably couldn't tell just by looking at it. So yeah, you want to avoid that. You use time commands, and then yeah, that's our solution.
So there's one last question.
So all of your examples were using like the Python UHD interface. If I'm using GNU Radio blocks, what's the best way to interact with the GPIO and
Yeah,
control it?
I think the other gentleman just mentioned that. So obviously C++ or C will let you do that as well. The GNU Radio block has, I think you can send messages to it to toggle that. So it's using the message passing interface. Like I don't know the exact API, but I'm sure that's like I think that's probably in the manual actually. I know not everything is documented, but I'm pretty sure that is. So yeah, you send a message command, and you can include a timestamp, so you can do like time toggles that way as well. And there is also a Python API exposed through GNU Radio that you can use, and it does the same as the UHD API. But the message commands, I think that's sort of the most GNU Radio-ish way to do that.
That's true, and also stream tags, right? If you
Yeah. If you, so the stream tags so in general, like stream tags and messages, they can do the same thing. So you can do in-band or out-of-band messages into a block, and then they will be executed on time. That's probably it, right, Marcus?
That's totally right. Yeah.
Okay. Well, thank you again. And did you have the next speaker? Can I hand the mic to someone?
So give a warm hand of applause for Martin, and